Hi everyone, this is the second video for section 2.1 on sets. So we left off talking about the cardinality of a set, the empty set, and a set being well defined. So now we're just going to make a few notes about subsets and sets being equal. So one thing to note is that every set is a subset of itself, right? And so we're going to denote this with X is always a subset. Let me write that a little bit better. Is always a subset of X, right? Remember the definition of a subset is if something is in X, then it's in the thing it's contained in, which is in this case X. And also, we also have that the empty set is a subset of every set X, right? Because everything in the empty set, well, the empty set doesn't have any elements. So this is an example of something that is vacuously true. Remember we talked about vacuously true when we did truth tables in section 1.3. So this is something that's vacuously true because every element in the empty set is an X because there's nothing in the empty set to check. Okay, so those are just a few quick notes about subsets. So now we're going to talk about two sets being equivalent and the difference between equivalent and equal. So two sets are equivalent if and only if, right? That's that biconditional. If they have the same number of elements, that means that they are equivalent. So, for example, we have the set ABC, and we say that they're equivalent using this tilde, that same as the not symbol, that this is equivalent to 1, 2, 3. So two sets are equivalent if they have the same cardinality, essentially. They can be placed in one-to-one correspondence, where A corresponds to 1, B corresponds to 2, C corresponds to 3, a one-to-one correspondence. Just meaning they have the same cardinality says that two sets are equivalent. So now two sets are equal if they have the exact same elements. So remember we talked about above that the difference between sets and sequences is that A, B, C is the exact same thing as C, B, A, right? They both have the letters A, B, and C, just in a different order, but because these are sets, the order doesn't matter. And one other special set to note, well, so that's the difference between being equivalent, just means they have the same cardinality, and being equal means they have the same elements. Okay, so now we can consider a universal set. So everything we deal with has this underlying universal set. So that's the set of all elements being considered is this universal set written as U. So this is just important because if we're dealing with sets of cats and sets of dogs, that all lives in the universe of animals. And our universe can be different, right? We can be talking about a set of cats and a set of dogs, and our universal set can be animals, but our universal set could also be living things, right? And that's two different universal sets. So we just need to, sometimes the problems we do will depend on, the universal set may be important to the context of the problem. But whenever we use Venn diagrams like these to denote sets, our universal set is always going to be this big box out here, U, that contains our sets that we're dealing with. This is going to be our universal set, is this box. Okay, so now we kind of shift gears a little bit and talk about operations on sets. So now we're going to talk about set operations. Okay, so we have the first one is intersection. So the intersection of two sets A and B is the set of elements common to both A and B. So you can see the intersection is denoted by this symbol, which whenever we talked about the logic in the previous chapter, we saw that this was really similar to the logical and symbol. That's because this is similar, right? It has things in both A and B. So if we have this as our set A, and we have this as our set B, the elements that are in A and B are right here in this overlap, right? A and B. So next we have union of two sets A and B are the sets of elements that are in A or B, or both A and B. So A or B. So remember that or, well, this is a symbol for union. The symbol for or was, instead of this U, it was a V. So again, we have our universal set, we have our set A, and we have our set B. So be careful whenever you're writing out problems like this, that the U for the universal set should look different than your symbol for union, right? I have this little tail, right? This little tail that you can do on the universal set that's not on the union. So even though the union looks like a U, make sure that it looks different than your symbol for universal set. So now the union of these two sets are the set of elements that are in A, right? So the things that are in A, the things that are in B, but also the set of things that are in A and B. So this just takes everything in the circles and we look at all of it. So you can see that the union and the intersection aren't quite opposite operations, right? They both contain the things that are in both A and B. So just one thing to note, these aren't opposite things. Yeah, they have this overlap, which is precisely the intersection. Okay, so the next operation we can do is complement, which logically corresponds to not, because it takes the elements that are not in A. So it's just, yeah, all the elements in the universe that are not in A. So if that's our set A, then the complement is everything outside of A. So we can just take everything here outside of that A circle that's still in the universe that we're talking about. So that's the complement of A. It's everything that's not in A, right? So this is really similar to our logical negation. And so one thing to note about this, just if you've taken any other math classes or whenever you eventually teach your own math classes, is that notation in mathematics is not consistent. That may be frustrating for you, but it's just kind of a fact, right? People don't always agree on how things should be written. So complement can be denoted by this bar, right? This bar over A, but it can also be written as a little prime for A. Sorry, that should be more vertical. A prime for A. Some people do it as A with a little c to denote complement, or some people write it as the universal set minus everything in A. Yeah, so it just kind of depends on who's writing whatever you're reading, how they denote it. But mostly for this course, we'll write it with the bar on top. But just be aware of those different things. So the next operation that we have is set difference. So this one is the set of all the elements in A that are not in B. So this is that minus that I just wrote for U minus A. We're going to actually explain what that means right here. So if we have still our same universal set, and we have our set A, and we have our set B, let me rewrite that U. The set difference is the things that are in A that are not in B. So we want the things here in A, but we're not going to shade anything that overlaps with B. So we're not going to take that overlap with B. So that's going to be the set difference. So everything in A, and we subtract out, take away everything that was also in B. Okay, so one last thing is sets being disjoint. So two sets can be disjoint if they have nothing in common. So compared to all of these other diagrams we've had above, this one doesn't have anything in the overlap of those two circles. So if we have our universe, we can have A in B, and there's nothing in their intersection, right? There is no intersection. So one way that we can write this is that A intersect B, what would normally be the overlap of those circles, that is nothing. So that is the null set or the empty set. So A intersect B, the things that are in common to both of them is nothing. Okay, so those were the operations. So I'm going to keep going to do these. Well, I'm actually not. So I'm just going to stop there with the different set operations. Hopefully these all make sense to you. Yeah, but that should be it. We'll pick up next time with these examples, but that is all for this video.